Okay. Hello everyone, teachers, students, and everyone present here. I'm delighted to be a part of this forum focused on solving agriculture problems through research and innovation. Today, I will be presenting on the topic of the balance of the evolution, Magnaporthe origin. My name is Mengtian, um, and we all know the Magnaporthe origin, common as rest blast fungus, is a devastating pathogen that affects rice crops worldwide. The rapid evolution of this fungus poses significant challenges in developing effective strategies to control its spread and minimize crop losses. And we can say in our laboratory primarily focused on exploring the interaction mechanism between the rice blast fungus and the plants. In our recent research, we made an interesting discovery by looking at the ISW2 gene in the rest blast fungus. And we can look at the picture. This one, we look out these genes, and the gene look out by homologous recombination. And in the pictures, we can see when we look out the genes, they lead to decrease in growth rate and reduce spore production. And to test the growth rate changes under different stress conditions, we add SDS and so on. We observed that compared to the wild type, the growth of the mutant was strongly inhibited. And to assess the pathogenicity, we conducted in calculation on rice and barley plants. Significant lowered pathologist towards both rice and barley compared to the wild type. So based on these findings, we embarked on investigating the underlying mechanism, which uncovered a higher meaningful story. And so we aim to understand what specific function lies behind it. So we find the first we find the ISW2 is located between two nucleosomes and is responsible for pulling and moving nucleosomes, thereby regulating genes in the vicinity of nucleosome. And then, based on the transcriptome date and the chip date, we have found that MOSW2 genes appear to contribute to the adaptation to both biological and non-biological changes. When the two nucleosomes come closer, genes that are responsible for rapid adaptation to environmental changes, and these changes are spliced, leading to a slower pace of evolution. So, uh, we can say when the rice blast fungus evolve, and the plants also lead to evolve in order to resist it. So therefore, when the evolution of the rice blast fungus slows down or can be controlled, the gene-for-gene hypothesis may be challenged. It implies that plants' resistance against the rice blast fungus will become easier to achieve. If the gene-by-gene hypothesis is challenged and broken, it could have the following benefits for agriculture. The one, enhance the group resistance by breaking the gene-by-gene hypothesis. Alternative genetic mechanism can be utilized in agriculture to enhance crop resistance against the disease, pests, and environmental stresses. And the two, accelerated breeding processes. So if the gene-by-gene hypothesis is no longer the slow factor influencing genetic processes, scientists and agriculture researchers can explore other genetic mechanisms to improve crops more rapidly and accurately. And the three, increase the crop efficiency. Challenging the gene-by-gene hypothesis may lead to enhanced crop efficiency. This can manifest as increased yield, improved water use efficiency, enhanced nutrient absorption, and other advancements to meet the growing demand for food from global population, and therefore increase the diversity and adaptability. Breaking the gene-by-gene hypothesis may result in more random genetic combinations and mutations, thereby increasing genetic diversity within crop populations and improving their ability to adapt to different uh, environmental